Now, dear students, chapter number 8, Gravitation, and today we have the topic escape velocity. And to understand the concept of the escape velocity, first we are just throwing an object in a vertical upward direction, and we can see it if the velocity is not sufficient. So it is possible that it can be fall back towards the surface of the earth. Now we are just maintaining sufficient velocity and we are just throwing it, so somehow it can possible that it never comes back towards the surface of the earth. So we can understood that why it is possible, because it left the gravitational field of the earth. So at this time this sufficient velocity is called the escape velocity. So on behalf of the basic define, we can understand this one concept. Now here we can take the one of the basic define the escape velocity is the minimum velocity with which a body must be projected vertically upward so it just escape gravitational field of the earth. So here we are just discussing the planet that is called the earth, and from the earth how much escape velocity is needed to throw an object, so we want to discuss that one. For it, I have made the concept that the earth which having the mass a capital M and the radius that is capital R, and from its center O, or from the surface of the earth we are just taking an object which is lies at a distance x. And so the OP is the x is there, and the mass of the object which we want to throw it, that is small m, is there. Okay, so the small amount of the work done, we are just finding always that the small amount of the work done to take an object from P to Q, and where we are just throwing this one object from the radius r. This is the portion of the radius r we have up to this. Suppose this one is a point that is called the a dash is here, and this is the r is there. So we are just taking we are just taking this one object from the radius r to up to infinity, so we will produce the integral is there. Okay, so this is the basic concept through the diagram from where we want to make the calculations one by one. So here we have made the basic concept. Consider earth of mass m, capital M, and the radius r, where the object of mass m lies at a point P, where we can imagine the OP is equal to x is there. Force of attraction on the body is at the P is. So we can assume the force of attraction, and capital G, capital M, small m is that x square is the force of attraction we have. Okay, now a small amount of work done, a small amount of work done to carry an object from P to Q, as P to Q is there. So we are just making the small displacement is there, that is called the dx, and the small amount of the work done, that is called the dw for this process. Okay, so we are just imagining the simplest formula of the work done here. So we can say that dw is equal to f dx we have. This is the equation number 2, and at the place of the f we can use that dw is equal to capital G, capital M upon x square is there with the multiplication of the dx. Okay, now we can apply the limit. This is the equation number 3 we have. Now the finally we are just taking this one object between the two limits, where we have the initial limit, that is capital R, and definitely it's a portion of the surface of the earth to the infinity. Okay, in the interstellar space is there. Okay, so we are just taking the total amount of the work done for this process. So the W total can be stated as capital G, capital M, small m, and we have the relevant integral r to infinity 1 upon x square dx is there. Okay, so this is the simplest present representation of that part, and we are just assuming that G capital M small m minus 1 upon x that means r to infinity is there. This is the total amount of the work done, and whenever we are just summarizing it, so the total the full explanation of this term, it comes in this manner: 1 upon m uh, minus sign is there, which I am just keeping outside. 1 upon infinity minus 1 upon r is there. So this one is the simplest, as we are just making the concept that work done, that is called the minus, that minus minus plus is there, finalizing. Finally I am just getting that minus g capital M upon r is there. So this is the kind of the work done we have needed to project an object from the r to infinity, and this is the equation number 4 we have. Okay, now this kind of the work done will be impart to produce the kinetic energy. Now the kinetic energy given to the body to perform this work done. So we have the concept of the kinetic energy, that is called the half mve square is there. So by the law of the conservation of energy, we are just saying that mve square by 2 is there. Now we are just separating the meaning of the ve there. Ve is nothing but it's simply the symbolic notation of the escape velocity we have. So I am just keeping here 2g capital M upon r is there, as we can further changes it to g capital M upon r is there. So this is the simplest general formula we have, or the first formula which represent the concept of the escape velocity. This is the equation number 5 we have. Now we can make the several changes in it by the replacing the sum of the terms. Now, as we know that the object which is lies on the surface of the earth at a distance r, which having the small mass m, so there is a force of attraction on this body, and the weight which acting the downward, so we are just making the mg is equal to capital G m upon r square. So we are just replacing g is equal to gm upon capital R square, and at the place of the gm we can write the gr square is there. So further there is a needful change comes in the formula in the equation number 5. So this is the first formula. This is the another formula, as we are just using gm, capital Gm is equal to gr square. So we are just getting the another formula in term of ve is equal to under root 2 gr. So this is the one of the another representation of the formula we have. Now we can also replace the concept of the mass is there. So by mean we can construct the another formula. Now we are just constructing the formula number 3rd, as at the place of the mass of the earth we are just assuming the density of the earth can be given rho is equal to capital M upon 4 by 3 pi r cube. I am just replacing the capital M, that comes rho into 4 by 3 pi r cube. So I am just using this one in the equation number 5. So I am just getting the another formula. VE is nothing but it's a simply 2 capital G by R, and the M is nothing but it is simply the rho into 4 by 3 pi R cube. So we are just getting the another formula. So VE comes in the part of whenever I am just making the complete solution of that term. So it comes that 8 pi rho G by 3. So this is the complete formula of the escape velocity. So we have the three basic formulas of escape velocity. VE is equal to under root 2 gm upon r, that is equal to 2gr, that is equal to 8 upon 3 pi rho g r square. So these are the three formulas we have. Okay, three consecutive formula we have, and as per the need we can use them. Now what is the escape velocity? If you are just talking about the escape velocity from the surface of the earth, for an object which we want to proceed it. So we will discuss it. So we have the simplest representation that VE is equal to under root 2GR, and the certain values we have regarding to the earth, that from the surface of the earth we have the acceleration due to gravity, that is called the 9.8 meter per second square, with the concern of the radius that 6400 kilometer, or either we can make the conversion of this radius into the meter. So we can write that 6400 times to power 3 meter is there. Okay, then after we are just making the representation of these terms in the formula, so we are just getting 11.2 times to power 3 meter per second, and same how we can say that 11.2 kilometer per second. Okay, so this is the necessary velocity which we have required to escape an object from the surface of the earth. Okay, now what are the important parameters those are necessary to explain, and how the escape velocity depends upon the certain factors. Okay, so we want to discuss them one by one. Now, as per the discussion of the formula, we can say that the escape velocity depends upon the mass, that capital M, and the radius capital R of the planet from where body just projected. Okay, तो जिस प्लानट से हम उस बॉडी को प्रोजेक्ट कर रहे हैं उसके मास के ऊपर डिपेंड करता है, उसकी रेडियस के ऊपर डिपेंड करता है. The escape velocity does not depend upon the mass of the body which projected vertically upward. Okay, so any kind of the body which we want to proceed from the surface of the earth, and we are just asking that it does not allow to come in towards the surface of the earth. So all the time we should follow the basic that mean velocity, that is called the 11.2 kilometer per second from the surface of the earth, because we can see that each planet having the different mass and the different radius, so the escape velocity is the different for the different planets. Okay, now point number third. Now the V does not depends upon the angle of the projection from the surface of the earth. For it we can say that as the earth is make the rotation about its axis, so it is very much easier to attain the escape velocity along the direction of the earth in which it rotates. So this is all about the escape velocity. So today we have discussed the concept of the escape velocity, the minimum velocity which is required to escape an object from the gravitational field of the earth, and we have a standard velocity from the surface of the earth, escape velocity, that is called the 11.2 kilometer per second. Okay, so this is all about the escape velocity, and we will discuss the numericals also in the coming lectures.